The relative molecular masses and boiling points of some fuels are shown in Table 22.1. Part A. Write an equation for the incomplete combustion of heptane. The general structure of an alkane is CnH2n plus 2. Heptane has 7 carbons, so has the structure of C7H16, because then that's following the general formula. Combustion means a reaction with oxygen, and it's incomplete combustion, which means that we produce carbon monoxide and not carbon dioxide. Carbon dioxide is complete combustion. But we also produce water. So now we need to balance the equation. We need 7 carbon monoxides because we have 7 carbons. And then we need 8 waters because we've got 16 hydrogens. And then balancing the oxygens, we need 7.5. To get the mark for this question, you must have the full equation correct for the incomplete combustion of heptane. Part B. Explain the difference in boiling points of the fuels in Table 22.1. If we start by comparing heptane and hexane, heptane is a longer carbon chain than hexane, so it has more points of contact. So this is going to be our first bullet point and our first marking point for this question. So then our second bullet point or marking point is that because heptane is a longer carbon chain, that means it's got stronger induced dipole-dipole interactions because of its more points of contact. So that's our second marking point. And then our third marking point is that pentan-1-ol can form hydrogen bonds which are stronger than induced dipole-dipole interactions, because the more energy is required to break hydrogen bonds over induced dipole-dipole interactions. So to get the 4 marks for this question, there are 4 bullet points that I'm writing here, and each of these bullet points is a marking point for this question. And as you can see, the bullet points correspond with the boiling points because more energy is required to break hydrogen bonds, which is why pentan-1-ol has the highest boiling point, and that heptane has stronger induced dipole-dipole interactions, which is why it's got a stronger boiling point or a higher boiling point than hexane. So it follows the trend that we're shown in Table 22.1, and therefore we're making sure that we're answering the question correctly and to our fullest potential. Fuel additives are often used to improve the combustion of a fuel. Part 1. Compound N is a fuel additive containing carbon, hydrogen and oxygen only. Complete combustion of 1.71 grams of compound N produces 2.97 grams of CO2 and 1.62 grams of H2O. The relative molecular mass of compound N is 76.0. Calculate the molecular formula of N and suggest a possible structure for the compound. The first thing we're going to do in this question is work out the moles of carbon dioxide and water using the equation triangle of mass divided by relative formula mass times moles. So if we start with carbon dioxide, we're given its mass of 2.97 grams, so 2.97 divided by 12 plus 16 times 2, so that's the relative formula mass of carbon dioxide, gives us 0.0675 moles. Then doing water, so we've given its mass of 1.62 grams, so it's going to be 1.62 divided by 1 plus 1 plus 16, which is the relative formula mass of water, and that gives us 0.0900 moles. Then we need to work out the ratio of carbon to hydrogen. So carbon dioxide to water is 3:4, but there are 2 hydrogens in water, so that means the actual ratio of carbon to hydrogen is 3:8. So then we can work out the molecular formula will be C3H8, and then we need to work out how many oxygens there are. So we can use the relative molecular mass of 76 to work this out. So that would be 76 minus 12 times 3 plus 8, which equals 32. And then we need to divide by 16 because that's the formula mass of oxygen. So that's going to be 32 divided by 16, which equals 2. So we have 2 oxygens. So now we need to suggest a possible structure. So we could have 2 alcohol groups, which could be at the end of our carbon backbone chain, and then we fill the rest with hydrogens. Alternatively, you could have the oxygens in between the chain. So you could have carbon, oxygen, carbon, oxygen, carbon, and then your hydrogens, just so long as you make sure that the molecular formula of C3H8O2 is shown in all your structures that you present, but you only need one possible structure. But either are fine. You could also have the alcohol groups in different locations along the carbon backbone chain, as long as you have the correct molecular formula shown in your structure. To get the 5 marks for this question, you get a mark for working out the moles of carbon dioxide, a mark for working out the moles of water, a mark for working out the ratio of carbon to hydrogen, not a mark for working out the ratio of carbon dioxide to water. You get a mark for working out the molecular formula of N, and a mark for a correct possible structure of N. Part 2. Sulcitol has been investigated as a potential fuel additive. Sulcitol is synthesized from propane 1,2,3 triol and a carbonyl compound. Construct a balanced equation for this synthesis. Show structures for the organic compounds in your equation. So let's start by drawing propane 1,2,3 triol as our first reactant. So we have our carbon backbone and our 3 alcohol groups at carbons 1, 2 and 3. Then we have a carbonyl compound that we're reacting. So the carbonyl compound that we're using in this question is going to be a ketone, and it's going to be propanone. And then we're going to form our sulcitol, so we can draw this out again, just copying what's given in the question. And this is what's called a condensation reaction, so we also produce water as a byproduct for this reaction. To get the 2 marks for this question, you get a mark for identifying that the carbonyl compound is propanone, and then you get a mark for the rest of the equation being correct. Part D. A scientist is researching compounds that might be suitable as fuel additives. One of the compounds gives the analytical results below. Elemental analysis by mass: carbon 54.54%, hydrogen 9.10%, oxygen 36.36%. The mass spectrum has a molecular ion peak at MZ 132.0. The proton NMR spectrum in D2O, where the numbers by the peaks are the relative peak areas. When the spectrum is run without D2O, there are 2 additional peaks with the same relative peak areas at 11.0 ppm and 3.6 ppm. Use the information provided to suggest a structure for the compound and show all your reasoning. So our first step is going to be to work out the molecular formula, and we do this by working out the empirical formula and then using the mass spectrum data. So working out the empirical formula, we need the elemental analysis by mass. So what we do is we take each percentage, so 54.54, 9.10 and 36.36, and then we divide by the relative atomic masses of carbon, hydrogen and oxygen. So for carbon that's 12, for hydrogen that's 1, and for oxygen that's 16. So for carbon that equals 4.545, for hydrogen that equals 9.10, and for oxygen that equals 2.273. Then we divide by the smallest, which is 2.273, and we do this for each of the values we've calculated. And then we get a ratio of 2 to 4 to 1. So that means we've got 2 carbons to our 4 hydrogens and our 1 oxygen. And this is the empirical formula. Working out the molecular formula, we need the mass spectrum data. So this has a relative formula mass of 12 times 2 plus 4 plus 16, which equals 44. And we've got a molecular ion peak of 132. So we do 132 minus 44, or divided by 44, sorry, and that equals 3. So our molecular formula is going to be our empirical formula times by 3. So that's C6H12O3 is our molecular formula for our compound. So if we look at this hydrogen environment 1, so that's got a chemical shift of 4.0 ppm and a splitting pattern of a quartet. So this could be CH3CHO as an environment that it's connected to, and the hydrogen that would produce this would be this hydrogen here because it's got a 1 next to it, which means that there's 1 hydrogen in this environment. So looking at number 6, so this has a chemical shift value of 1.3 ppm and it's got a singlet splitting pattern with 6 hydrogens in this environment. So this could be CH3 brackets 2 connected to a carbon, and the hydrogens that would give this peak are these ones here, the hydrogens attached to this carbon with 3 of them around it. So now moving on to 3. So this has a chemical shift value of 1.2 ppm and it's got a doublet splitting pattern with 3 hydrogens in its environment. So it could be CH3CH, where the hydrogen responsible for this would be these hydrogens here. Again, the hydrogens attached to this carbon where there's 3 of them. The way that you can identify the splitting patterns is you look at how many hydrogens are next to your hydrogen. So for the first environment, you've got 3 next to it. So you're going to have 4 lines because it's how many's next to it plus 1. So your singlet, you've got none next to it. So you're going to add 1, which means you've got 1 line. And then in your doublet, well, you've got 1 hydrogen next to your environment. So you add 1 to 1, so that means 2. So you've got 2 lines, which is a doublet. Now looking at our D2O peaks, we have 1 with a chemical shift value of 11.0 ppm and 1 with a chemical shift value of 3.6 ppm. So we can use our data books for these. We know that D2O is going to remove any oxygen-hydrogen peaks. So we look for ones with an OH in their group. So the chemical shift value at 11 ppm, that's a carboxylic acid, or COOH. So the hydrogen in question is this one on the end. And then at 3.6 ppm, this is an OH peak. So the hydrogen that is removed is this hydrogen here. And now we can suggest a structure for this compound. So we need to make sure that we've got the molecular formula correct and we're meeting all of these hydrogen environments. But we can label them after we've suggested a structure just to double check that we've got everything correct. So if we have CH3 connected to a 3 carbon backbone with a carboxylic acid on the end, and we have our alcohol groups. So already we've met the D2O peaks. And then we have CH3, CH3, and a hydrogen to make sure our molecular formula is correct. So now we can look at the hydrogen peaks and we can label them. So starting with our D2O peaks, we have our 11.0 ppm hydrogen here in our carboxylic acid, and we have the 3.6 ppm hydrogen in this OH group. So then looking at the first hydrogen environment, we have this quartet. So this quartet is going to be this hydrogen here, a 4.0 ppm, because it's connected to our CH3, so we're going to have a 4 hydrogen splitting pattern. So now looking at number 6, so this number 6 is going to be a singlet, and it's going to be these hydrogens here, so 1.3 ppm and 1.3 ppm, because that has 6 hydrogens, because we've got 3 and 3, so 6, and the carbon it's connected to doesn't have any hydrogens attached to it, so it will have a singlet splitting pattern. And finally, our doublet, that's going to be this one on the end with our 1.2 ppm, because it's connected to a carbon with 1 hydrogen, so it's going to have a doublet splitting pattern. So we've checked that all of the data we've been given matches the structure that we've suggested. Because the molecular formula is correct, we've got 6 carbons, we've got 12 hydrogens, and we've got 3 oxygens, so that's correct. And we've double checked that all of our hydrogen environments match the hydrogen NMR that we've been given in D2O and the 2 additional peaks without D2O. So this is a level response question, which means that there aren't set marking criteria. Instead, to get the 6 marks for this question, the suggested structure shown must have a C6H12O3 molecular formula that's consistent with the splitting pattern and chemical shifts in the NMR spectrum. And you must have comprehensive reasoning with most of the data analysed. So in this answer here, we've analysed all the data and we've shown that we've confirmed that the NMR spectrum peaks match our suggested structure. So this would get 6 marks.